Hello, hello. Oh my God. Hello, hello, Yanelli. Hello, Chastity. Good afternoon for the double Venita. Oh my God. Okay, that's a new one. Wait, and don't tell. Oh my God, it's been so long. That is Oh my God, I totally know that. Mimikyu? Is that no? That's Mimikyu, right? That's quite a picture. Is it? Yes. All right. Sweet, sweet, sweet. Um, um. Hello, Kaya. Good. Okay, I'm doing the chat now. We're just gonna get started in a second. I still owe you guys, and some of you I don't. Some of you, most of you I do, or many. Okay, good. But we're just we're just doing our best here to close the semester down with as much dignity and knowledge and success as possible. So yes. So good afternoon, Venita and Mimikyu. Good afternoon, Yanelli and Yanelli. Good afternoon, Gabriella and Gabriella. Good afternoon, Genesis and Genesis. Good afternoon, Kaya and Kaya for the double. Good afternoon, Chastity for the double. Good afternoon, Natalie and Yasminina. And good afternoon, Direct Chat. Good afternoon, Carlos. Good afternoon, Sydney and Skylar. Yes. Okay. Okay. I'm just going to. Oh, and good afternoon, Brian. Okay. Okay. Um. Oh. Yes, they're coming one at a time. I apologize. I know this is the same. Hold on a second. One second. Hold on. I know someone's in the waiting room. Just one second. Uh, okay. Um, okay. I'm just gonna get to it with the material. Um, yeah. Oh. Okay. Okay. Sorry. Sorry. I'm responding to the direct chat. Uh, but here we go. But I'm just gonna get to the material. But if there's more questions, feel free. Yeah, okay. Um, this is what we have to get to today, like right now. Um, um, so here we go. And this is material that's flowing from everything we've been talking about, electrostatics, flux, the field from a wire is what we did 2 days ago. This now is the next step from that, but it's now off homework. Like we're beyond the homework now. Everything I'm saying, I just want you to know Could it be on the final? Yes, maybe. We'll talk about that on Monday. Like we'll talk about the final on Monday. Um, so are you maybe responsible for this material? Yes, but is there any homework on it? No. So just try to understand it as best you can, please. And for what it's worth, I think it's actually the most exciting material in a way. It's sort of what brings everything that we've been doing, in my mind, it brings it all together. But whether or not it does, here's the story, or here's the content. Well, the content is something called Orsted's finding. But oh, I've already well, um, shouldn't have had that written. But before I even say about Orsted's finding, let me remind you of a couple of things that you've learned this semester that you need in the back of your mind, like for this discussion. First of so one, two, three. One, first, please remember that earlier in the semester, and you may want to take notes on this. Like everything I'm about to say, I've said before, but I want to put it in focus now, sort of efficiently. So I'm not going to write it all down, but you may want to. Like, remember number one, earlier in the semester, um, we said that when vectors are involved, there's three different ways that multiplication can occur. Way number one, when vectors are involved, is you can multiply a vector by a scalar. If you multiply a vector by a scalar, what you're in effect doing is taking an arrow of a certain length in a certain direction and you're changing its length. You're scaling it up, or you're scaling it down. You're stretching the arrow or you're shrinking the arrow. So whatever you do, you end up getting a new arrow that is still an arrow. In fact, you get a new arrow that's in the same direction as the old one. So when you multiply a scalar by a vector, you get a vector every time. Furthermore, so we said that like months ago. Furthermore, that is a way that you could sort of understand any vector, a vector of length 5 and direction 45 degrees could be understood as a, a vector of direction 45 degrees with a length of 1, i.e., could be understood as a unit vector pointing, a unit vector of length 1 pointing in a certain direction times uh, a scaling number like 5, right? So we often say like a vector equals a times a hat. A vector is a unit vector scaled up or scaled down by a certain amount. So first way of doing multiplication is multiplying scalars by vectors to get vectors. And in fact, any individual vector can be thought of that way as the product of a scalar times a vector. Okay, that's way number one. Then way number two was you could take a vector and multiply by another vector in a manner that produces a scalar, right? And when you do this, it's called the dot product. And if you're multiplying a vector by another, if you're multiplying a vector by another vector in a manner that produces a pure scalar, what you're trying to do is measure the relationship between the two vectors that, in the end of the day, can minimize the role of direction, right? So what you're doing when you do a dot product is you're measuring the extent to which both vectors agree on direction. You're only measuring the component of one vector that lies along the axis of the other vector so that you could sort of just treat them as two numbers on a number line. So that's why the dot product of vector A and B is magnitude A times magnitude B times the cosine of the angle between them. So dot product produces between two vectors produces a scalar and thereby measures parallelism. Now we use the dot product a lot in this class so far. I mean, in two big ways. Dot product was number one used to calculate, to define work. Work is the integral of the dot product of force with displacement, force vector with displacement vector, right? So that's a dot product. And then flux, electrostatic flux, was the double integral of the dot product of field with area. So that also was a multiplication of two vectors that produced a scalar. That was dot product. Then we learned about this third thing called the cross product, which was what you do when you multiply two vectors together in a manner that produces a vector. That's the cross product. And in the cross product, you really are focusing on direction. You're focusing, you're trying to capture the directional information and preserve it in some way, take it into account in some explicit way in the final answer that you get. The final answer is a vector that has magnitude and direction. And so therefore, in the scalar, in the cross product, you're looking at the extent to which two vectors differ in direction. You're looking at the extent to which direction plays a role in their relationship. So it measures how perpendicular two vectors are. The magnitude of the cross product between two vectors A and B, remember, is A magnitude times B magnitude times the sine of the angle between them, as opposed to cosine. So the cross product measures perpendicularity between two vectors and therefore produces a vector that is itself perpendicular to both of the original vectors being crossed. Like, remember this, and that's the way I'm saying it here, reminding you is like the unit vector I crossed with the unit vector J produces a unit vector which points along the K axis perpendicular to both the original two axes. The cross product produces a vector that is aligned with neither of the axes of the two original vectors. The direction of it is determined by what we call the right-hand rule, right? Now, technically, I'm reviewing, like we did this, we practiced this cross product earlier in the semester, but we never saw it used in any physics. There is a reason that we did it early in the semester. We're about to see today. So I want you to remember it before we go any further. Okay, so that's point number one, the cross product. Point number two. Okay. Point number two, Coulomb's law, on which all of this Gauss's law and all of this flux and everything is based. Coulomb's law, I mean, I know you know it, we use it all the time, but I want you to stare at it for a second and realize something about it that you might not have noticed before. Coulomb's law, I just want to see, did I make a picture? No, I didn't. All right, Coulomb's law determines the electrostatic field vector at a point in space over here due to a point source of charge somewhere over here, right? And the whole idea is we're trying to figure out what's the field vector sitting right here in space due to the charge point over there. Field is a vector. Realize that, like any vector, realize that the vector that it is can be thought of as a product of scalar with vector. Like the way to think about the electrostatic field vector over here is you look at the point source over here, you draw a line in your mind, R, the displacement that points from the original point source to the field point. And then from that displacement, you construct a unit vector, r hat. R hat is a vector of length 1 that specifically points in the direction from the original charge Q to the location P, right? So you've got this unit vector R that's pointing in that direction and telling us the direction. Then you scale it up by a magnitude determined by the constant, the electrostatic constant, times the amount of the charge over here divided by the square of the distance from here to there. So this displacement vector R contains the information R direction and the information R distance. Both of those pieces of information, the distance and the direction, are explicitly being taken into account in the E field vector in a manner that allows you to look. I want you to see that the E field vector is produced by a scalar point. The E field vector over here is produced by a zero-dimensional scalar called charge. And, and by being produced by a point, it can be viewed as a unit vector scaled up by a certain amount. It is a scalar times a vector. That's what the E field is. And it's produced by a point. A point has no dimension and a point has no direction. Okay, so just bear that in mind in the back of your mind. Okay, now, last thing, something that you know not from me, but you know from lab, you can set charges in motion. Like more specifically, last week, 2 days ago, we were analyzing a line of charge, right? A lambda dq per dx, a bunch of coulombs per a bunch of centimeters, right? Line of charge. Now, all the analysis we did Monday, the Gauss's law and everything, was to determine the field nearby due to this line of charge sitting around. But as you know from the lab, you can set this line in motion and create what we call an electrical current. If you set so look down here at the blue at the bottom of the page. If you set the lambda, the line of charge, in motion with some v, you now have what we call current. And what is lambda? Lambda is dq dx. What is v? V is dx dt, right? So the dx's cancel. And at the end of the day, what current is defined to be is dq dt, meaning current is a continuous flow, a continuous velocity of charge lines. And if you stand somewhere, I mean, that's what's flowing through the wires in your lab right now. If you stand there and stare at a point in space and count the amount of coulombs that pass by that point in space per unit time, you're measuring current. Current is dq dt, derivative of charge per unit time. 1 ampere of current means 1 coulomb of charge per 1 second of time. An ampere is a coulomb per second. Current is the time derivative of charge. Okay, I just want you to know that. I mean, I think you do know that from lab, but I'm putting it in your mind, or pointing to it in your mind. So with those 3 facts in your mind, consider something that happened in the early 1800s. Well, in a lot of labs around the world, people were playing with circuits, primitive, basic circuits like you are in the lab. Recently, the voltaic cell had been invented, by Volta. So now we have these power sources, these limited power sources that set electric potentials that set charges in motion through resistances and create these circuits that obey Ohm's law. And it's pretty exciting. And there's a lot of a new analysis to do on this new piece of technology in the early 1800s and stuff. And in a number of labs, but primarily including this lab of Oersted set up 2 currents, isolated them from he set up 2 wires. He isolated them from other effects. He put them nearby each other. And at first, he didn't turn on the current or anything at all. He just had 2 wires, 2 lines of charge, like Monday we were analyzing. And as expected, nothing interesting happened when there was just wires sitting there with just charge static. Oh, yeah. Question? Okay. Then he turned on the juice. He turned on switches so that batteries, voltaic cells, motivated current flow through each of these wires. So now I1 is a current going across the lab like this, and I2 is a current nearby. It may or may not be the same magnitude, but it's definitely the same direction. 2 currents nearby each other, isolated from other effects, same direction. And what Orsted found, what Orsted observed, as you may know from high school or from seventh grade or something, what happened was, and you also might know because it was written here a second ago, what happened was that the two wires came together. They attracted. Now, this is a big deal. And then, of course, he reproduced it over and over again under, controlled conditions. And then in other labs, this was reproduced over and over again. And this could be, it wasn't a fluke, in other words. Two parallel current carrying wires attract. Now, is this a surprise? Yes and no, or no and yes. No, it's not a surprise in a way, because if it were a complete surprise, he wouldn't have set the whole thing up. Like, there was some reason to believe. Oh, and by the way, when I say attract, I mean without touching each other, right? They just like move toward each other. They seem to be pulling on each other through empty space. Now, is this a total shock? No. Um, we are already, he's playing with electrical charges. We already know electrical charges can affect each other through empty space. That we know electrical charges are in wires. He knows that. So so he's obviously looking for something. He's sort of may have some reason to expect or believe that when he turns on the current, something's going to happen between these two wires. So in some sense, it's not a shock, but it is a surprise. And here's why. This is action at a distance. This is attraction through empty space, right? Now, first of all, now we're familiar with that. Generally, whenever we see action at a distance, we call it a field. We're familiar with fields at this point in physics history. We're certainly familiar with the gravitational field. We know that things can, that masses pull on other masses without touching each other. But the gravitational field is not what's going on here, for the simple reason that these wires didn't come together when the current was off. Like, there's a whole bunch of protons and electrons in each wire. They all have mass and all of that, but evidently not enough or to overcome whatever forces are holding the wires in place. Uh, when the current wasn't on, the masses didn't attract. So gravity is not what's happening here. Then you turn the current on and then they attracted. So it has something to do with the moving charges. Now, we do know that extra protons attract extra electrons and vice versa. And the wires do have protons and electrons in them. But there weren't extra protons in one of the wires. There's no reason to assume they were. It wasn't like anybody's finger got sparked when you touched it or anything. And furthermore, if there were extra protons or extra electrons in one of the wires, they would have attracted before you even turned the current on. They didn't. But then he turned the current on. He started getting the charges to move, and they attracted. So you could say something like, well, I guess now that they're moving, maybe they're getting bunched up together more, or maybe they're getting spread out more. So maybe somehow the charge density is changing in the wires since they're now moving. Like, maybe by moving them, we've done something to the amount of them per unit space that we didn't realize. And so that's causing an electrostatic field. Could be, except here's the big, and maybe honestly, that's probably maybe what he was thinking, might something like that might happen, and that's why he set it up in the first place. But the big hook, the big surprise is that whatever you're doing to the top wire by moving the charges, whatever you're doing to get them more bunched together or more spread apart or something, presumably that exact same thing is happening to the other wire. So whatever you're doing to one, you're doing to the other. So if the wires were going to do anything now because of the motion of charges through it, they should have repelled, right? What we know about electrostatics is that likes repel and opposites attract. So what I'm trying to say very definitively is ultimately the direction of this action at a distance is a total surprise. Ultimately, the fact that this happened over and over reproducibly was not a prediction, does not follow from logic. It forces us to come up with new logic. Like, seriously, like, this is not the result of any law that we've seen so far. This means there must be a law that we don't know about yet, right? Let me be more specific, and I will turn the page. There's action at a distance between these two wires. That means that each of these between these two currents. So that means that each of these currents is creating a field. I mean, if field means what field means action at a distance. So each of these currents must be creating a field. It can't be a field that it's not one of the fields that we already understand. It's not gravitation. It's not electrostatic. Our understanding of those fields cannot explain why these wires would go together rather than apart. The fact they go together rather than apart is so surprising that, of course, they tested it and they flipped the wires around, like and did various combinations. And sure enough, when you put the wires in anti-parallel, they repel. So in effect, they're doing the exact opposite of what you would think they would do if this were a purely electrostatic phenomenon. So there must be a field happening here that we have not yet, as physicists, analyzed or studied or mathematically deconstructed. There is a field here that is worth investigating. This field, whatever it is a field that is not caused by masses. It's not caused by masses sitting around and existing. It's not caused by charges sitting around and existing. It's caused by charges moving. In order to observe, which we've never been able to at a micro level do before technologically until this point in history, into the early 1800s, let's say. How do we get charges to move around? We move them through thin pieces of conducting material through metals, right, known as wires. So there's some kind of field caused by charges when they move. And the easiest way to observe or consider charges moving is through metals. So they could have called this field anything. They could have called it the Oersted field. Like they're going to analyze it now. We're going to analyze it now. This new field that we're going to try to figure out the math and the pictures for and everything. It's a new field. We could call it anything. We could call it the Oersted field, but they realize, well, wait a second. There's this other action at a distance that people have been taking advantage of for millennia that we've never talked about yet in physics. There's this one other phenomenon where things affect each other without touching. And this other phenomenon is ancient in terms of its usage. An iron hunk, if you put it near another iron hunk, attracts. And if you turn one around, like with these wires, it'll repel, right? And little iron filings attract iron hunks, and little iron needles seem to attract to the iron core of the earth, i.e., compasses, right? So people have been making compasses and toys out of certain pieces of metal, iron, that seem to do something like this for centuries, and we use them operationally. People have been using compasses in an effective manner for a long time, but no one's ever worked out a mathematical or microphysical theory for any of these iron hunks that have been attracting and repelling each other since the dawn of time. So Oersted and his people, in a sort of in a hopeful, conjecture kind of way, in the spirit of physics, where we would like to try to explain the greatest number of phenomena with the fewest pieces of information, right? Where we'd like to not reinvent the wheel every time and hope that our old methods can capture new data until they can't. They say, aha, this new field, we're going to call it the magnetic field. Of course, you saw that coming. But I want you to understand this is where we're going to say from now on, there's a field that moving charges create, and we're going to call that field the magnetic field, sort of in recognition of this magnetism that's been going on for centuries, but that everybody uses, but nobody understands. Like really, like certainly not on a mathematical or micro level. No one has a field theory for magnets at this point, or field line diagrams or anything like that. So they say let's call this field the magnetic field in the hopes that it's not a coincidence that, in other words, let's call the field that's caused by moving charges a magnetic field in the hopes that eventually somehow our understanding of that would lead us to explain and understand why it is that certain kinds of metals attract and repel other metals. And let me tell you, let me jump to the chase on that. Indeed, it does. I'm not going to wait. I'm not telling you all this to spin your wheels. It turns out to be right that the reason iron hunks attract and repel other iron hunks is that, very quickly, is that all objects are made of atoms, right? And all atoms have protons in the nucleus, but then have electrons going round and round in orbitals outside the nucleus, right? So any given atom actually is a little natural circuit, right? Any atom has an electron going, or a bunch of electrons going round and round and round, and creating a current loop in a norm, which means any atom is a tiny little mini magnet. Apparently, like it has current going around it that is creating a little bit of magnetic field, because apparently magnetic field is the field that is created by moving charges. But in most materials, all the atoms and all the orbitals are aligned in a totally random haphazard, well, maybe not random, but in a haphazard way. So you've got a magnet like go here, and then another magnet over here, and another magnet here. So you got magnetic field pointing that way, pointing that way, pointing that. So in a normal, statistically, in regular everyday materials, even certainly non-metals, but even lots of metals, all the little magnets are not lined up, and they cancel one another out. But in certain kind of metals like iron, it turns out that all the little magnetic directions either are already automatically lined up or can get lined up very easily. So it's what it turns out to be true that a hunk of iron is a bunch of current loops all lined up so as to reinforce all the little magnetic field contributions, and it ends up being one big magnet. So, okay, so from here on in, what I want to say is, from what we want to say is, static masses cause gravitational fields. Static charges cause electrostatic fields. Moving charges cause magnetic fields. On an elemental level, if you have a charge with velocity, you create that is a little magnetic field. So now we want to analyze that field mathematically formally. And for weird historical reasons, we designate the magnetic field with a capital B. I know it's weird, but we do. Like electric field is E, gravitational field is lowercase g, magnetic field is capital B. Okay. The question now is, what is the field vector function to describe what is the function to describe the magnetic field? Like, what's the equivalent of Coulomb's law for magnetic field? Okay. We're going to build our concept, we're going to build our function from the model that we already have of an electrostatic field. Like, so I'm reminding you again. I'm reminding you that the electrostatic field is like a constant times Q over R squared times R hat. I'm reminding you again that by R is a vector that can be understood to be a magnitude times a direction. R is the displacement vector that points from the point source to the location of interest. I think, in fact, and I'm not saying you have to memorize that constant, but just remember that constant is just a constant to make the units work out. Like so. Oh, wait, okay, hold on. And let me just say this and then the chat. But just notice one thing: like the stronger the charge, the stronger the field, and the closer the charge, stronger the field. But then there's like this whole vector subtlety that I want to remind you of in a second. But wait, there's something in the chat. I know. Hold on. But why can't I find it? Hold on. Okay. Huh. Huh. Good question. Yeah. I never quite thought about it exactly that way, but yes, I mean, really many parallel circuits, but yes, the circuits are parallel, not series. That's good. Oh, I see, because you're in the lab now too. Yeah. Yes. Yes, good question. Um, okay. All right, so I'm going to here again. I know, and I see. I'm just trying to drum in exactly how to picture the electric field because I need it to make a contrast to the magnetic field. So I'm up here as a picture, reminding you again, like you have a point source Q here. That's the blue thing. You're trying to figure out what the electrostatic field is up here at point P. We're ultimately trying to determine or calculate or predict the electrostatic field vector, the red thing, at point P. What I want to try to reinforce to you again is like a way to think about it is first in your mind, draw the displacement vector from the point source to the field point, from the point source to the location of interest. Draw a displacement arrow. That's called R vector, right? Well, our vector has a magnitude and a direction. The direction is r hat. Like r hat is r vector divided by r, meaning once you've looked at this displacement, once you've looked at the direction and distance between the charge and the place that you're looking, from there you could, in your mind, construct a unit vector. You could take a vector that has length 1, but specifically points in the direction of r, right? So this is the yellow thing I'm talking about now. R hat would be a little arrow of length 1 pointing from Q to P, and it's there to like signify specific direction, the direction that we're looking at, the direction that we're looking at from the thing causing the field. Um, it's the direction that we're looking at, but it specifically has a magnitude of 1, so it's not going to affect multiplication or anything like that. So we look at that unit vector and then we scale it up by the amount 1 over 4 pi epsilon naught q over r squared. Like the distance, the pure distance squared is what goes into the denominator of this one big fraction, or this one big combination of constants, all of which is the amount that by which we scale up the yellow unit vector r. And in so doing, I'll make this a little longer just to make this clear. In so doing, we ultimately end up with this red vector, right, which is its own length, is what I'm trying to say. And that yellow vector, excuse me, that red vector that's sitting at point P, the field vector, has a length of 1 over 4 pi epsilon naught q over r squared, i.e., the bigger q is, the longer it is. The closer it is, the smaller r is, the longer it is, right? It has its own magnitude, but its direction is definitively the direction of r hat. It definitively points along the line between q and p, right? That's what the E field vector is. And please notice again, I know I've said it like 40 times now, but notice again, it's a vector that can be thought of in our minds. It's constructed by taking a unit vector and multiplying that by a scalar. It's vector by scalar multiplication, creating a vector that is caused by this zero-dimensional scalar thing called charge, called Q, the charge that's just sitting there at that point, okay? That's how the E field vector works. Now, we're calling magnetism a field. We're saying, oh my God, here's a new action at a distance. Apparently now charges that move, like the charges that exist, they're already creating their own electrostatic force, a field. Now we're saying, but if they're moving in addition to that, in addition to the electrostatic field that's already there, they're going to create this new field called a magnetic field. The magnetic field is a field, but that's being created by motion of charge. So the belief, the hope slash belief is if it's a field, it acts like fields. It follows all the rules, the math, the diagrams of fields, but whatever those would be, whatever the math and diagrams would be applicable to a moving charge. So we rebuild the old equation. We're like rebuilding the old equation according to the new information. What do I mean by that? I mean, we just go piece by piece. So I'm building, so now I'm at the bottom of the page building the yellow B field. And it's the same situation, right? Now I'm asking if I've got a moving charge over, I mean, it's almost the same situation. I've got a charge here in blue, but it's not just a charge sitting there. It's moving. It's got some random velocity off like that, right? And I'm over here at a point in space, and I'm asking what is the magnetic field vector over here at this point in space? Well, like how is it determined by the information causing it? So I'm going to build an equation for B vector, like along the model of what I already have for E vector. So first of all, in parentheses, it's going to be a constant, right? Now, it's going to be a constant that we assume it's going to involve 4 pi and all that, because if it's a field, it's going to spread out equally in all directions, like the surface area of a sphere. So we're going to want that convenience of having a 4 pi in there that'll cancel out with 4 pi r squareds and but right. So we figure there's going to be a 4. Now we're designing this now. I don't mean you and I are design, but I mean like back in the day, they could sort of design this equation from the convenience of already having the electric equation and hope it works. I mean, if it doesn't work, if it makes bad predictions in the lab, then they have to scrap it and try something else. But they're going to go with the simplest possible thing until it doesn't work. That's how physics works, or that's how physics functions. And everything I'm telling you does work. Like these are the right answers. I'm not yanking your chain. So they can design this equation. First of all, there's going to be some kind of constant that we're going to divide by 4 pi. It's not going to be the same constant as the old one. It's going to be a different constant. It's got to make these units work out. So it turns out this constant, we use a mu for magnetism. This one's called mu naught. It happens to be 1.27 times 10 to the negative seventh henries per meter, whatever. Um, but since we're designing this from the ground up, we have the convenience of putting it in the numerator, which is easier than the denominator. Like, remember, the other one we sort of discovered, so it just worked out, like, sort of inconveniently, that the epsilon naught was in the denominator. But here we're designing it. So we put in the numerator, 4 pi in the denominator, like before. So we've got a constant. Okay. Then what's going to go on the bottom? R squared, just like before. We're assuming it's a field. We're hoping, we're conjecturing that field spread out equally everywhere in space like a sphere. So we're assuming it's like every other field we know so far, gravity, electrostatics, we're assuming it's an inverse R squared function. So we put R squared in the denominator. And now we got to be now. Notice on the top, like in the white, the electrostatic field thing, we have Q times r hat, right? Meaning Q is the thing causing the field, Q is the charge, and and it's going to cause, that's the scaling factor on a vector, which measures how far away and in what direction we are from the Q. Like the E field vector is in strength is based on the Q, but in direction is based on the direction that we are from Q. That right, that's what the R hat means, that the field has to point along the line connecting the charge to the location. Okay, so same thing here. The thing that's going to cause the field has to be multiplied by the R hat, just like before. Okay, but the only catch now, and this is a big catch, I'm going to slow down now because like this is like the real heart of the matter, is like everything I'm just doing the same. I'm just mimicking our knowledge from electrostatics. But now the thing causing the field is not just a charge or a mass, it's a charge with motion. And by motion, I don't just even mean speed. I mean speed and direction. Remember, if the two wires were aligned, I mean, if the two currents were aligned, they attract. If one current was turned around, then they repelled. So, and if there was no current, nothing happened. So the motion was necessary. And then, by the way, to be honest, realistically, like the more current there was, the more this happened. Like there was clearly a dependence on the amount of motion, the V of each charge. But also there was a dependence on direction. If you turned around one of the wires, the whole direction of the interaction changed. So the thing causing magnetism is not Q, it's QV, where V is velocity. So what goes in the numerator of this equation isn't just a Q, it's a QV. Fine. Okay, so it's going to be QV times R hat. Fine. But notice V is a vector, and so is R hat, and so is B. B has to be a vector. B field is a vector. Fields are vectors. E field was a vector as well, but it was a very straightforward vector. It was a vector that was formed by taking a vector and scaling it up or down a certain amount. E field was scalar vector multiplication. The B field looks like it has two vectors involved forming it. I mean, it does. So now, for the first time, in other words, we have a field vector being formed by the product of two vectors. I'm going to say this again because it's such a big point. What causes the electrostatic field is a dot, a point source, a quantity with no dimension and no direction. A dot is what causes electricity. Now, what we have really, what causes magnetism really is a line of flow, a current. Now, what causes magnetism is a quantity that has dimension and more, maybe more important, direction. What caused electricity was a point. What causes magnetism is itself a vector. That changes the whole game. It means that we're now, even in our simplest construction or understanding of how the magnetic field works, like even in our hope that it is as simple as it could possibly be, even in our hope that the magnetic field will just follow all the rules of fields that we've already established with the electric field, right? Even in that simple game, we have two vectors up in the numerator of the equation of the function. And we were asking ourselves to multiply one vector by another so as to produce a vector. Well, there's only one way to do that, right? I mean, there's only one way to multiply vectors and produce a vector. That is called the cross product, right? So apparently, so I just wrote the same thing again, but I put it in there now. Apparently, the law that determines the magnetic field in the most elemental, simplest possible case, the law itself contains a cross product. This law, and it's correct. I mean, I'm saying this all like they were building it and thinking of it, but yes, this was a building and a conjecture. It's a design of an equation, but then it does turn out to work. I mean, that's why we're learning it. So this equation is the magnetic equivalent of Coulomb's law. It's the equation that tells you the magnetic field in the simplest, most elemental scenario. Most elemental scenario here would be a little bit of charge moving, or better, a little bit of current flowing. This law is called the Biot-Savart law. That maybe that might help you remember the fact that it's called B, even though I don't actually think that's really the reason. But the law is named after these two French physicists, Biot and Savart. Okay, so this is the magnetic equivalent of Coulomb's law. But I'm making a big deal of it because I'm saying now there's a cross product in there. First of all, that's why we had to learn about cross products early in the class. It wasn't just to like, give you busy work. But second of all, I mean, it's a good thing that we learned about cross products because to have a cross product in a fundamental law means something sort of surprising. Remember, the cross product of two vectors is a vector whose direction is determined by the right-hand rule. I'm saying, I mean, you probably can't read my handwriting. I mean, it says at the bottom, the direction of the B field is determined by the right-hand rule. It points neither along nor it points neither along V nor along R hat. That, I mean, even I can't read that. Hold on 1 second. Okay. This means we now have a field that doesn't point along the axis of like either of the two things that caused the field in the first place. I'm going to be specific and physical in a minute, but like, I mean, remember, the right hand rule says if you want to do the cross product of V and R, you place your fingers along V, you curl your right hand, you place your fingers along V, the first vector, you curl them toward R, and wherever your thumb points, that's the direction of the answer. In this case, if charges are moving like that, and we want to know what the field is down here, we curl our fingers from there to here, and our thumb is the B field, which means this original picture that I keep saying, it seems so stupid when I keep, like, even to me. I mean, it seems like such an obvious point that I keep saying, like, if the charge is over here and you're over here, you get pushed by a field that pushes you that way. Like, and if you were like negative, I mean, if you were like an electron, you get pulled that way, right? But the point is that the field and resulting force point along the line connecting you to the original thing making the field. It seems so, like, what else could it be, right? I mean, it's like duh, like if I'm pushing you and you're over there, I push like this and you accelerate that way. Like if you're over there, I don't push like this, right? I push like that. It seems so. And so the mathematics of it is that's what the R hat means, that the direction of the field is in the direction of R hat. Duh. Except it turns out not to be a dub, because it turns out that some fields don't do that. The magnetic field doesn't do that. The magnetic field evidently, well, here's the example. Like, oh, let me pause. I'm going to say this example, but let me back up to say a piece of notation also. Like now, because of the right hand rule, we have no choice but to be thinking in three dimensions now. Magnetism forces us to think in three dimensions. And of course, my page or the board is only two-dimensional. So what do? We a piece of notation from now on, whenever you think of vectors, I mean, yeah, when you think of vectors, imagine them as like arrows, as like medieval arrows that have tips on the front and have like tail feathers in the back. So if an arrow were coming out of the computer screen at your face, or like out of your page at your eyes, you would just see the tip of the arrow. So something's coming out. So look at the bottom of the page right now, like in the white. If something's coming out of the page, we draw like a circle with a dot in it, meaning you would just see the dot coming at you. But if something was going into the page, because it's like hard to draw, right? If something's going into the page, you imagine you would just see the cross section of the tail feathers in the back of the arrow. So we draw an X. Okay, so from now on, X means like into the page, dot means out of the page. And what I'm saying here is if you picture that original experiment that motivated all of this, Orsted's finding, like there's like charges rushing along in a wire. Apparently, if the charges are going like this and you're down here under the wire, we are saying, like, if charges are flowing, if current is flowing through the wire, then you're at some point in space below the wire. There's magnetic field created by, I mean, there's magnetic field everywhere from these moving charges. It's field. I mean, the field is everywhere. But if you want to look at specifically point by point what the field is doing, if the flow is like this and you're down here looking and you want to ask what's the field doing, well, you apparently have to do the right hand rule. You put your right hand along the V, you curl the right hand down along the R, and the field points in the direction of my thumb. It points in to the computer screen, points into the board at point P. In other words, the B field apparently doesn't pull down, like even though the wire is above you, the B field isn't pointing down. Then you might say, well, I mean, I guess because the wire and the current's going like that, so maybe does the field pull like that? No. Apparently, the field points in a direction that has nothing, as little to do as possible with where we're looking and what direction the flow is going in. It's like crazy in a way. I mean, it's not literally crazy, but it seems at first like very surprisingly complicated. We are saying the field is a cross product, the magnetic field. It obeys the right hand rule. The magnetic field, due to a flow in some direction. I mean, a flow at some displacement from us will point in a direction that is neither along the flow nor along the displacement. That is what I'm saying. I mean, I'm going to try to make it more clear in a minute. We still have 20 minutes. Um, but before I go any, I'm trying. I'm trying to say two things at the same time. There's two sides of my mouth. On the one hand, I'm saying you're if you can only appreciate the impact of what I'm saying if you find it a little bit weird. Like if you don't think what I'm saying is at all weird, I don't think you're hearing me. Like it should be a little surprising, a little bit confusing at least. Like I'm literally saying that if they are there under the wire, the field is not pulling me up toward the wire. And I'm saying the field is not pulling me to, I keep saying wire, I mean current. If there was a current passing to the right and I were underneath it, I would find magnetic field that does not pull up and does not pull to the right, but in fact pulls in the third direction, pulls like in, like south or whatever you want to say. If you think that's a little strange or you're like, what is he even saying? Then you're probably with me because that is not how electricity works and it's not how gravity works. And it does seem really odd. Of course, I need to make sense of it. But the first sense I want to say is, well, right, this is different because what's causing the field is already a directional quantity. Like electricity and gravitation were just little dots. A little dot's over here, it's going to pull me toward it. Like, put another way, if there's a little dot over here and I'm over here and I'm experiencing field from that dot, that means I'm experiencing the information representing the size and location of that dot, like representing all of the vital stats of that dot. What are the vital stats of a dot? The vital stats are how big the dot is and where it is, right? So there's one direction involved in that concept, the direction of where is the dot. If the dot is to the south of me, if I am to the north of the dot, then the field points north. Like the only direction to care about is the direction of where am I relative to the dot. So the field captures that information and spits it out in an arrow that points to the north. Here, on the one hand, what seems crazy is that the field seems to not be capturing the information of either of the two directions that seem like the vital stats describing the situation. But that's where what's mysterious about seemingly confusing about it is exactly the point. It's exactly why this happens, is that here now we are like south of the dot. The dot is north of us. That's one piece of directional information. But now it's not good enough for the dot just to sit there. If it's just sitting there, it's not causing magnetism. Now the dot has to be moving to cause magnetism, and it has to matter what direction the dot is moving in. Like if it moves in one direction, one thing's going to happen. If it moves in another direction, another thing's going to. So now I'm north of the dot, and the dot, say, is moving east. Those are the two pieces of information that have to be communicated to the point in space over here. Two vectors have to be crossed. Two pieces of directional information have to be somehow communicated to this point in space. If either one of them was weighted more than the other, well, I mean, if the field over here pointed more in the direction of one than the other, it would be weighting the information of one direction more than the information of the other direction. That can't happen. And if the field over here did point in the direction of what literally pointed in the direction of the flow, it wouldn't be taking into account at all where we were. I'm saying there's two pieces of direction that have to be taken into account equally. So the only way to do that, the only way for space here to know, oh, something's happening like this over there, is for the information itself to come in the form of an arrow that points this way along the third remaining axis. Like I'm going to move on, but this is a very big point. I'm saying the magnetic field always points in a direction that has nothing to do with the direction of the displacement or the direction of the flow. That's what's weird about magnetism. But I'm also saying it's not weird when you really think about it, it really makes sense that since there are two directions to take into account, the only way to know there's an X thing happening and a Y thing happening is for the answer to land on Z. If it landed on X or Y, we would not catch the other axis. So the magnetic field from moving charges obeys the right hand rule and points along the axis that is neither the QV axis nor the R hat axis, as in this example. So, okay, there's 15 minutes left. So that's what I'm saying so far. It's on you. In fact, yeah, actually, let me go one step further with that. Everything I just described was like the point underneath the wire. Like, what about a point above the wire? Well, same logic. If there, I mean, there's got to be field everywhere, but the fields are going to be doing different things depending if you pick different R hats. So if you're above the wire, above the current's going like this, but you're above it, you do right hand rule. If the current's going like this and you're above it, then my thumb points um, the other way out of the board, right? So if you were above the wire, the current would point in like that. I'm sorry, would point out like that. And if you were in front of the wire, right? So those are two different field vectors. I mean, and again, that's not crazy. Like that's like electricity. If you were above a charge, you'd be pulled down, you'd be pushed up. And if you were below a charge, you'd be pushed down, right? I mean, every point, that's why we always have that sunburst picture. Like all the field vectors from an electrostatic, from a charge, they all radiate out in all directions. Well, something like that is happening here with the magnetic field vectors. I mean, they're all going into, but they're not radiating now. Like, look at it. If you're a point above, the magnetic field would come out. If you're a point below, the magnetic field would go in, the magnetic field vector. If you were in front of the wire, if you're in front of the wire is going like this, right hand rule, my fingers curl to you, then my thumb would point up. So if you were in front of the wire, the magnetic field would point up. I just did that wrong. Oh, no, sorry. If you were in front of the wire, sorry. If you were in front of the wire, might feel I'm getting front and back confused because of screen and all that. But like if you're in front of the wire, my fingers would point along the wire and curl in front. So then my thumb would point down. If I were behind the wire, my thumb would point up. So look at it like above, it comes out. Then in front, it goes down. Then below, it goes in. Then behind, it goes up. Like, what are these vectors all doing? They're all looping around the wire, right? They're not bursting out like radial lines. They're all curling around the wire because they're all obeying the right hand rule, right? So, in fact, I'm getting ahead of myself in a way here a little bit, but what I want you to notice right now is we're following all the rules of fields. We're assuming that if the magnetic field is a field, then it does everything fields do according to whatever's causing them. So all the rules of drawing magnetic field lines and everything pictures will be the same rules as drawing electric field pictures, but the simplest possible magnetic field picture will look very different from the simplest possible electric field picture. What I'm trying to say in so many words is electric field lines burst out radially from points. Magnetic field lines loop around lines. Magnetic field lines are always closed paths. They don't have sources and sinks because there is no source or sink. There's no point that's creating this. There's flow. There's a vector that's causing this. So the simplest, most symmetric picture that could possibly be produced by magnetic field lines is closed paths. Loop, like if this line were perfectly straight and infinitely long, the magnetic field lines around it would be perfect circles. If the line's like a little bent or something, then they might not be perfect circles, but they're all loops. Magnetic field lines form loops, closed paths. Very different picture from electrostatics because, again, electrostatic fields are caused by points, by non-dimensional, non-directional magnitudes, scalars. But magnetic field lines are caused by vectors, directional, dimensional quantities. Therefore, electric field lines burst out of points, magnetic field lines loop around arrows. Okay, we're almost done, but and that's funny. That's a surprise. I didn't see that coming. They didn't see that coming. It may even seem sort of weirdly complicated, but it's the simplest possible picture given this requirement that apparently we have a field now being caused not just by stuff, but by stuff in motion. The only question that remains for the last 10 minutes is, but wait a second, how does all that explain? Well, or I'll say, how does all that explain, or how is that any consistent with with this? Like what I'm arguing, if you're following me, I'm saying like that wire on the top is creating a magnetic field below it that's all sticking out of the board, and a magnetic field below it that's all sticking into the board. So why the heck does the bottom wire go up then? It sounds like I'm contradicting myself because I am saying the field does not pull up or does not point up. Yet the bottom wire seems to accelerate up, seems to be forced up. So vasti stat, like, so what is going on? Good question. What's happening to the bottom wire is that it's responding to the force from the field, of course, right? Like field just sits there. Like if you have an electrostatic field and you put a mass in an electrostatic field, you've got an electrostatic field, you've got a mass, that's fine. But the mass doesn't care. The mass it won't accelerate or anything. It has to be a charge to experience a force from, like, only charges create fields and only charges experience forces from fields. Let me say it one last way. The whole field picture is I create a field, then the field exerts a force on you, right? It's a middle agent. I don't exert forces on you anymore. I create a field, the field exerts a force on you. That's the whole idea. That's the whole idea. And so you have to be the right type of object to create the right type of field and vice versa. Masses create gravitational fields, then masses experience gravitational forces. Charges create electrostatic fields. Charges experience electrostatic forces from the field. And similarly, moving charges create magnetic fields. You got to be a moving charge in order to experience the force from a magnetic field, right? So look, to remind you, like, so the question is, so how does the bottom wire get forced up? I mean, if the magnetic field is pointing in, why does the thing get forced up? Well, electric field is force per charge, right? I'm just reminding you. Therefore, force was charge times field. Remember that? Like, field is how many newtons are being exerted per each coulomb of charge. So if you then put 2 coulombs of charge in the field, the amount of force experienced is that many newtons per each one. So if the field was like 3 newtons per coulomb, but you put 2 coulombs in there, the total force experienced is 6 newtons. So I'm saying field is object time. No, I'm not. I'm saying if field is force per object, then force is object times field. So it's got to be the same thing with magnetism. Like with the magnetic force has to be magnetic source times magnetic field. But again, the magnetic source is a QV now, not just a Q. It's not just a scalar anymore. It's a vector. And the magnetic field is already a vector. So the only way a vector times a vector is going to produce a force vector is if it's a cross product again. So I'm saying first, a moving charge creates a field with right-hand rule. Then a moving charge in a field experiences a force from right-hand rule. So it's 2 right-hand rules to explain. If we see an interaction between 2 wires, we got to do 2 right-hand rules. I'm saying, is this? Yeah. I'm saying, I'm saying this. The magnetic field that was caused follows a right-hand rule. But then the magnetic force that is caused by the field also can follows a right-hand rule. So look at the original picture. First, we have a current up here, right hand. First, we have a current up here. It's it's going to create magnetic field everywhere, but let's look below it, down here. So we do the first Biot-Savart law. We do the cross product of QV with R hat. QV is going like this. R hat is going down because I'm underneath the current looking up at it. So we got QV going like this. We are underneath R going like that. So the field B is pointing in to the page. In is pointing the way my thumb is. Okay, that's what the field is doing. That sort of funny, surprising thing of pointing along a third axis. But now we put a current in that field. We put the second wire in that field. And the second wire is going to experience a force from that field. What's the force? The force is a cross product, a right-hand rule of QV cross field. So the second wire is moving like that, but it's in a field that's going that way. We just established that. So this wire is in a field that's going that way. So it's pulled along my thumb up toward the first wire. And if you did the same thing and if you do the same thing in the opposite direction, you get the same consistent. So I'm saying it works. I'm saying the wires attract each other because each one makes a field that is in an odd direction, but then each field makes a force that's in an odd direction. And in effect, two rights make a wrong. I mean, two wrongs make a right. Two rights make two wrongs make a right. And in fact, not literally, they're not wrong, but you get what I'm saying. And you could see it the other way too. If you look at the bottom wire is going like this. So above it, it creates a field where my thumb is going that way. Now the top wire is going like this in a field that's going that way. So my thumb points down. Um, so the bottom line of all this, the bottom line is that the magnetic field is a cross product. The magnetic field is created by moving charges and points along a direction that is neither the direction of the movement nor the displacement from the movement. But then the magnetic field causes a magnetic force that is also in neither the direction of the movement nor the field itself. So magnetic field lines are always at right angles to the things that cause them and to the forces that they cause. All magnetic field lines are all right angles. So at the end of the day, this is what I said a second ago, but since this applies everywhere in space, in the end of the day, magnetic field lines always form closed paths. Again, static charges cause E field lines that radiate out in all directions. Moving currents, flowing charges cause magnetic field lines that loop around in all directions. Magnetic field lines don't start or stop anywhere ever. They are always closed paths. That's the takeaway of this. Now, there's 2 minutes left. We're done, but I just want to ask you or plead with you or remind you, you may have noticed it's that time of year. It's time to do course evaluations of the course. Of course, you don't have to do them. I just want to emphasize, and I always find this all very awkward and everything. I just want to emphasize, and you don't have to do them, but it actually really helps if you do. I'm even on the committee that manages these things. I have been for years. We do not know who does that. I will never know who you are. I never want to know who you are. We never look at the individual ones or the individual. We don't get the name. Like I promise you that your anonymity is more protected than you know. But I also promise you, I partly because we don't want to know, but we can't even if we did. But I also want you to know that they matter more than you think. They really matter. We actually care more than you think. We care so much that it makes me nervous to talk about them. Okay. So I'm going to ask, so technically there's 2 course evaluations for this course because you've lecture and recitation, even if it's the same guy, same content. So they could both be the same. But if and when you get a chance, I may try to make time next class if I can. But if and when you get time, you'll see it in Google Classroom linked. Please do 2 course evaluations for this class. And then if you just screenshot the evidence that you did it, not what you did, just the check that they gave you for having done it. If you just screenshot that, you'll get 10 points for each of the evals you do. And I promise I won't look at them. I can't look at them even if I tried. But please do them and you'll get extra credit for having done them. Okay, yeah, thank you. Have a good day.
All right, thank you.
Thank you. Thank you.